In this video, I will demonstrate how to create confidence intervals for population means using the TI graphing calculator. In this first example, we have a situation where a study is conducted to learn about the average number of hours per week adults in a community spend on leisure activities. We have a random sample of 20 adults, and the time spent on leisure activities is the variable, and that time has been recorded. Now, in this problem, we're given some output from a software package called SPSS. And I think that stands for Statistical Package for Social Sciences. I could be wrong about that. I'm doing that from memory. I didn't look it up, but it's something like that. So SPSS is, there are many different statistical packages out there for different areas of study. But in any case, this is one. And what we have is the output. Now I'm going to go ahead and create this confidence interval on the calculator to show you how it works. First question here, though, I want to talk about the SEM, the standard error of the mean. Now, in the reading assignment that goes along with these lectures, I point out that the standard error is adjusted by the sample size. So we have two things going on here. We have the standard deviation, and we have the standard error of the mean. And this can get a little confusing. The standard error of the mean has already been adjusted by dividing by this number by the square root of n. So if you took 4.04, let me get the calculator going here. If we take 4.04 and divide that by the square root of 20, we get 0.90337. So this number's been rounded off, but that's what it is. So, and again, this number adjusts downwards as the sample size goes up. And in fact, we're going to use the standard error of the mean to calculate the confidence interval. It's a bit tricky, though, because this is not what we're going to need to input into the calculator. So I'll go through those steps in a minute. The other issue we have with this problem is that there are a couple of different distributions that are used when calculating the confidence intervals for the mean. One is the Z distribution, which is a standard normal distribution. The other is called the student's T distribution. And again, in this class, I wouldn't get into all the mathematical details about those two things. The one thing I would like to say and point out is that the T distribution is the one I recommend using for all situations involving population means. And the main reason is because it has less assumptions associated with it. And it's never incorrect to use the T distribution. So let me show you how to do this. So we're going to press the Stat button and scroll over here to Tests using the right arrow key. And then we're going to scroll down to T interval. And notice there's a Z interval here and there's a T interval. And that's what I'm talking about with the two different distributions. So we're going to use a T interval and press Enter. Now there's two options for inputting the information. If we just were given the 20 data points, then we could put those data points in a list. And once we've done that, then we could put the list name here and then specify the level of confidence and continue. In this particular problem, though, we're given the summary statistics. So I select stats, and notice it's asking for the pertinent statistical value, such as the mean. And this is the sample mean. It doesn't say sample mean in the output, but it's based on a sample, therefore it's the sample mean. This is the sample standard deviation. That comes from right here. Now, I could understand why it might be tempting to put 0.9 in here, but what we really need to do is use the standard deviation. And the calculator will calculate the standard error as part of the process of calculating the interval. So I put sample size here, and then we're doing this at 95% confidence. Press one more arrow down to calculate, press Enter, and notice we get the same exact interval that SPSS printed out. Now, I do want to illustrate one thing as we're working on this problem. Now, one of the ideas that that we've worked on is that as the level of confidence increases, the width of the interval also increases. So notice if I wanted to increase the level of confidence to 99%, and I were to calculate that interval, notice this is now a wider interval. Not terribly wider, but still wider in this particular example. So the next part of the problem asks us to explain what the 95% confidence level means in terms of repetitions. And this can be a complicated thing to understand. The basic idea here is that the only way we can have 100% confidence in our estimate from a mathematical point of view is to just say the interval is from like negative infinity to positive infinity. Anytime we restrict the interval's width, we're going to bring in some perhaps very small but yet non-zero chance that we've missed that population mean with our confidence interval estimate. And so the 95% number means that 95% of the intervals that we would calculate in this way would capture that true mean value. That means 19 out of 20 of these intervals capture the true mean, 1 out of 20 misses. On any particular estimate or attempt, we don't know if we've actually captured the mean or not. Let's do another example. In this example, we have like a natural resources kind of example, looking at the lengths of cuckoo eggs. We have a set of data here for this example. So we're going to do one now where we're given the raw data. So the first step in calculating this confidence interval will be to enter all these data values into a list. So to find the list editor, we're going to do an intermediate step here first. So press Stat, go down to number 5, choose number 5, which will come up on the home screen, then press Enter one more time. Should say done. Your calculator should say done. Now we're going to go back to Stat and then choose Edit. And basically what that first step does is just sets everybody's calculator screen up. So you're going to see L1 through L5 here. And I think some of the 83s and maybe the older 84s, I can't remember if they show all these L1 through L5 here or not. But in any case, we're only going to use L1 for this example. Now I have some numbers in L1, so I'm going to go ahead and clear those out. To do that, I just moved my cursor all the way to the very top here, press clear, one more step by pressing enter, and those numbers are gone. Now to enter the data, I'm going to just simply enter those numbers one at a time. So I would start with 19.65, press enter, 20.05 is the next one. It's easy to make a mistake entering this data. I've read that the most common statistical mistake is a data entry mistake these days with computers. Okay, so that's the idea. You would enter these one at a time. Now, it turns out that I've already entered all of these data values in L2, so I'm just going to go ahead to save time instead of having you spending 5 minutes of video time entering the numbers. I'm just going to copy them over here from L2. So when you finish, you should have a complete list of this data in L1. Now, the problem that part A says summarize the data numerically, and the idea there is to give the sample mean and the sample standard deviation. And it also says to show the data graphically. This isn't part of your homework, but I'm just going to go ahead and do this quickly. I'm going to draw what's called a histogram of the data, and just again as an illustration. And then let's see, there's a shortcut for getting the right window scaling, zoom stat. So basically this is just a rough kind of a graph of the data. And what we're looking for here is that telltale mound shape that indicates this data could easily have come from a normally distributed population. And that's quite believable for this example. Many variables in nature tend to follow a normal distribution. But in any case, our main goal for this class is to calculate the confidence interval. And again, we're looking for a mean. We're trying to approximate the population mean. So I'm going to use a t-interval as before. Now, in this case, I'm not going to really focus on this, but in this case, some might argue that we could also use a z-interval. I think there are really two schools of thought about which one's the most appropriate. But the t-interval is the one that's always going to be a bit wider than the z-interval. So it's going to preserve that level of confidence every time. So I like to just use t-intervals. This time we're given the data, so I'm going to, instead of selecting stats, I'm going to select data. Now, the data is in L1, but suppose it was in some other list. Then what we would do is just clear whatever's here, whatever list name is there, and then just press second 1 to paste L1 in here. This number should be 1. Under frequency, just leave that at 1. There are some situations where that would change, but not for our class. So for us, this will always be 1. And what that means is every data point just counts one time. Next step is to choose calculate, and there's the interval. So our estimate for the mean, the true mean cuckoo egg length, and again, this is for all of these meadow pipit birds. So there's a large population. When I imagine this population, I'm imagining thousands, tens of thousands of birds, 100,000. I don't know how big the population is, but there are many. And so that of all those birds, what we're trying to do is estimate the true average, mean average length of those eggs. And we're going to put our average somewhere between 22 and 22.6 millimeters. And our confidence level is 95%. Now, there's one last part here. And so for part C, what does the interval tell us about the mean length? Well, it tells us that it's most likely somewhere between 22 and 22.6 millimeters. Are we positive? No. There's some room for error here. There's a 5% chance that we're wrong about that. But 95% of the time, 95% of these intervals will capture the mean. So I have high confidence, but I'm not positive. Finally, in part D, we're asked to whether there's evidence the mean length differs from 23 millimeters. And based on this interval, I would say yes. 23 is not within or between these two numbers. 23 is on the right side. It's outside of the interval. Therefore, I would say with 5%, what we call in stats level of significance, which is also explained in one of the videos, I would say that I'm, within a 5% error. I would say yes, we have evidence that these eggs are longer. The true mean average is shorter than the 23 millimeters that's being speculated on in part D. Okay, I hope you find this video helpful, and I'll see you next time.